So let's talk a little bit about figuring out the pH of a weak acid. As I think I mentioned in class before, when we calculate the pH of a weak acid, it's very much an equilibrium calculation. Except now we have the equilibrium of a weak acid. We have the chemical equation that corresponds to the acid dissociation constant Ka of that weak acid. And then using that, what we'll usually do is we'll use the equilibrium calculation to calculate the concentration of H+, and then based on that concentration we can calculate the pH of the solution. So here's our first problem. It's a fairly straightforward one as far as weak acid pHs go, and it's asking what's the pH of a 2.5 molar solution of acetic acid, and then it gives you the Ka of acetic acid as well. Not sure if we start this in ClarisNav. If you want to try to work through it yourself, feel free to pause the video, and then on the next slide I will take you through it and show you how to work it. Okay, so the first thing we have to do is set up the chemical equation. Write down the chemical equation that corresponds to the acid dissociation for our weak acid. And it has a general form of acid plus water goes to H3O plus the conjugate base of that acid. So that's shown right here. And then we make our ice table, just as we did in chapter 13. We have, we start with 2.5 molar of our acetic acid. We don't have any of the conjugate base or the hydronium ion. It comes to equilibrium in the process. Some of this acetic acid will react, and it's going to make X moles per liter of H3O+, and X moles per liter of our conjugate base. Then at equilibrium, we have these values. So writing down the Ka expression, we have the concentrations of our products over the concentration of our reactant. In this case, that would be the acid. And we get this expression, and that all has to equal the Ka of 1.8 times 10 to the minus fifth. Now, what we can do at this point, since this is such a low Ka value, usually when Ka is about 10 to the negative fourth or smaller, we can make a simplified approximation. And that approximation says that this X, this change in concentration, will be a lot smaller than what our initial concentration is. So if you take 2.5 and you subtract X from it, you're essentially going to get 2.5 back out. So what that allows us to do is it allows us to simplify the expression as just being X squared over 2.5. We can avoid the use of solver on the calculator, and it'll save us time. And so if you solve for X, you'll get X is equal to 6.7 times 10 to the minus 3 moles per liter. And then comparing the pH, we get pH of 2.17. So again, it's just a simple, straightforward equilibrium calculation. The trick is you have to make sure you have this this chemical equation correct. You need to make sure that you have your starting concentrations accounted for correctly, and then, if possible, you can make the simplifying approximation to simplify the Ka expression, and you can solve for X more easily that way. We can also go the other way with this. So if we know the pH of a solution, we can use that to calculate the Ka value of an acid. So the question, or a question we could have, is what's the Ka of an unknown weak acid if a 0.5 molar solution has a pH of 3.5? So if you guys want to work through that, feel free to pause the video and have at it. Okay, so in general, what we'll have is, again, this kind of standard equation for the Ka. Acid plus water goes to H3O plus A minus. Okay, that'll be our typical general equation. And once again, we will make an ice table, except with this time, when it says that you have a pH of 3.5 or whatever it gives you that pH, it's telling you what the X is. It's telling you what the equilibrium concentration of H3O+ and your conjugate bases. So by converting from the pH into a concentration, you're getting these final values. So what you can do is, you make your ice table, you actually plug in for X X will be this final concentration. So we'll plug that in here and we'll square it, and then we'll plug it in here and subtract it. And you can see here we could probably make the usual simplifying approximation again, because 0.5 minus 3.14 times 10 to the minus fourth will essentially give you 0.5 back. Anyway, we can keep it in there, and then knowing what all these values are, we can get the K expression, and we get a K is equal to 2.0 times 10 to the minus 7th. Okay, a problem that may arise is if you have a mixture of weak acids. So instead of having a single weak acid in solution, maybe you'll have two. Okay, and so how do you handle that? The thing that you do is you determine which one's the strongest acid, again based on what the Ka is. The one with the larger Ka will be the stronger acid. That will produce most of the H plus in solution, and so we'll say that that's pretty much going to be responsible for the H plus concentration. So we'll use the stronger acid to calculate the pH for the solution, and that's pretty much it if all you want is the pH. So if we ask what's the pH of a solution that has 1.5 molar HClO2 and 0.5 molar HNO2, and you're given these K values, you can see that this HClO2 will be a stronger acid than this nitrous acid here, HNO2. And so we'll use this concentration to do our equilibrium concentration, to do our equilibrium calculations, to get our H plus concentration and to calculate the pH from that. Okay, and you can see the work down here. So once again, we make this Ka equation. I can't emphasize enough, it's not that this is difficult, but you've got to be very comfortable with writing this chemical equation down, because it's not always going to be given to you in the problem. So we make our ice table. Once again, we'll use the starting concentration. We start with 0 moles per liter for each one of these. X moles per liter reacts to get to equilibrium. We plug all that in. In this case, because the K is times 10 to the minus 2, I don't want to make my simplifying approximation, so I'll just use my solver. I have X is equal to 0.13 molar. That would be the concentration of H3O plus as well as the concentration of ClO2. Knowing that, I can calculate the pH as being 0.89. Okay, but what if we want to then ask what will be the concentration of the nitrite ion in that above solution? In a sense, what has happened is that nitrate ion will come from the HNO2. However, the way we think about it is the HClO2 comes to equilibrium kind of first. In actuality, this is a simultaneous process. But because it is a stronger acid, it'll essentially establish the H3O plus concentration. So what we'll have is we'll have some initial concentration of H3O plus. This whole thing, still has to come to an equilibrium state and has to satisfy, the equilibrium condition. So when we make our ice table, instead of having an initial concentration of 0 for the H3O plus, we'll have an initial concentration equal to what the concentration was from the HClO2 solution. We start with 0.5 moles per liter of the HNO2 to come to equilibrium. Because we have nothing here, we still know that some of this will have to react to create some of this, and so we make our ice table. And we set up our equilibrium calculation once again, and you solve for X, and you get 1.5 times 10 to the minus 3 molar, which would be the nitrite ion concentration. Also, I want to point out at this point that assumption that we can kind of ignore the H3O plus concentration due to the HNO2 was a valid one, because this 0.0015 additional molar is added onto the 0.13. It's not going to be a big change. Okay, so if you want a more exact number for the pH, you could put this back in. However, it really is kind of fine just using the 0.13 molar for the pH. But we also find that the nitrite ion concentration will be 1.5 times 10 to the minus 3 molar. Okay, and so that pretty much finishes up for the calculation of weak acids. And if you guys have any questions, let me know.